So welcome back for the second round of lecture. So this is where we are going to discuss about the precision fermentation. So I gave you a bit of background on precision fermentation. We did discuss some part of it as we were discussing the cellular agriculture aspect. Now precision fermentation comes from this particular term itself, precise. It has to be very, very specific to a product. Now how do you make fermentation very specific to a product? You don't want anything else, but you just want the product that you're interested in. Is by making sure the host or the yeast or the fungi or the bacteria or the prokaryote or eukaryote that you're using in your fermentation process is only able to make your product of interest. That's what precision fermentation means, or precise means in this aspect. Again, as a part of the outline, I'll give you some background in the fermentation. We did had this conversation already, so I might go a bit quickly, or in case I can explain a bit more in that area. And then how the precision fermentation works, how it is done, what are the targets and the host selection. Now, what sort of host is required to grow what type of product is very, very important. The feedstock selection, we have been having that conversation as part of the question that you asked. And also the fermenter design, optimization, and the scale up. And then we'll talk about the application and the challenges and the industry landscape or the market landscape, how it looks like for precision fermentation. Now, fermentation-based production, as we have already discussed, requires sources which are your microorganisms like fungi, bacteria, algae, and the plant cells. You need to optimize the cells for the fermentation by optimizing the cell culture medium. Now, the question for you would be, so if you know that yeast will grow if I give a specific feedstock to it, right? So, if I give you yeast and I'm giving you the feed for it, so will you take this and put it in the fermenter directly, or will you start it at a lower scale, like in a lab first? What will be the process? Lab scale? Why lab scale? You have to activate it? Oh, you're activating the yeast? Okay. I give you activated yeast. You have to acclimatize your yeast to the production conditions, to the pH, to the temperature, right? And then you want to see whether the product is growing. Your yeast is growing enough and it is developing the product or producing the product, right? So that is done at the lab scale. So you do the culture. Once you have enough culture, you use that as a starter culture and you put that in the fermenter and provide all the nutrients for it to grow, let it grow, optimize the fermentation condition for it to grow, and then you have your product developed, and that's what you use. So acclimatization of the yeast to that particular raw material that you're providing is very, very important. The yeast can produce a product from different sources. So let's say, it's just a question because all of you have a background in biotechnology. Majority of you have a background in biotechnology, and you would have had a course in this. So let's say if I'm using a carbon source 1 and then I have a carbon source 2, will the yeast fail? Which source will it use first, C1 or C2? Why? Just because I am writing it as a C1? Yeah, but then how did you make a choice that it will use C1? I didn't say that C1 is the more likable by the yeast. So it will always use the carbon source that it likes. So it can be C2 also, right? That's why I said why C1. So it can be either of the carbon sources. When it has finished one carbon source, it will start using the second carbon source. But then it has to make modifications to its internal machinery, right? Its whole biochemical pathway has to change to accommodate that particular carbon source to grow. Am I correct? Because if you start eating one specific food product right now, okay, This was the best example. If you go to southern India, you eat idli sambar there, and if you go to northern India, you eat idli sambar there. They are two different idli sambars, right? If you're going to south, you cannot expect the same taste and the texture that you get in the north. If you go from the south to the north, you cannot expect the same texture and the taste. You have to get used to it. And that is the reason that acclimatization is required for any fermentation process. The type of carbon source that you are providing and the consistency of that carbon source has to be maintained for it to produce your product in a specific way. Am I correct in that? You're able to understand that aspect, right? So that's where the optimization aspect comes into for your cell culture growth or the growth of your host, which is going to produce a product. Then comes the fermentation, where your cells are added to the bioreactor with the culture media, and then they proliferate. So basically, you have already acclimatized it. Then you take that, put it into the fermentation. The fermenter is just used to grow it and make it big, increase the number. So first, lab scale, you have to do it at a small scale. You can use a 2-liter fermenter or a 5-liter fermenter or a 10-liter fermenter, and then you move on to a bigger, larger scale fermenter. Now, when you're doing this scale up, that requires a lot of mathematical calculations. We'll be discussing that later. And that's the reason the whole course that you will see, you have the bioreactor design analysis, which will be coming in the later days, where you will learn how to design a bioreactor. What are the equations? What is the mass balance required, the heat balance required to maintain a bioreactor or design the bioreactor for a specific product. And then comes the purification and the final product, or the proteins are isolated and purified. That's the downstream processing, right? Now they are used as food ingredients, or the products that comes out, they can be used as a food ingredient, they can be used as pharmaceutical products, right? They can be used as food beverages, that becomes a food ingredient too. So what we have understood is fermentation is very, very important, but it's a long process, not from the time perspective, but it requires different stages. That's what I mean by the long process. It has multiple stages. Now, we have already discussed this slide in the previous session that we had. So fermentation is key for the food industry because it can allow you to produce enzymes that can be used to add textures, color, or any profile, a sensory profile to your product, like tofu. It can be used to develop recombinant products like soy hemoglobin, which were used by Impossible Burger to make their Impossible meat or Impossible Burger, which was a meat alternative. They are also used for the growth factors for fermentation. Now, this is where I would really be interested in some of you in future can work in this area and use feedstocks, specifically the waste products or the food waste that we are developing or we generate every day. You know how much of the food waste is generated in the agriculture sector in India? How much of our agriculture produce is wasted in percentage? Guess. 10%, 20%, 30%, 1%, 2%, 30 to 40, 40? It depends. If it is somewhere between 40 to 50%. No, you're much more unique. You're giving me exact. Yeah, so it depends. It's 40 to 50%. It all depends on the cycle, the whole storage facilities that you have, the logistical facilities that you have, because you are going to generate waste at every stage of the food supply chain. Now, if all that waste can be used as a feedstock for your fermentation process, because they still contain the nutrients that can be used by the microbes to grow. So if you can use those as your feedstock, you would be able to reduce the overall cost of production. And you can, if you are able to use those to grow your growth factors, suddenly your production cost from $4 million will reduce to 200,000 or even less. Now, we have already gone through this application of the MRG foods, the classic cutlet. They also had crispy cutlet. I would really like you to go onto their website, themeaty.com, and look at the products that they have. If you have a phone or an iPad or a tablet right now, sorry, or even a computer, you should go onto their website and look at it. The products that they develop is really amazing. And it's really interesting how they do it. That is where the whole cell biomass is basically used. So because we did discuss that in the fermentation process, in the acellular, either it will be the product, the cells are producing only the product, or the cell itself is the whole product for us. They are also acting as a source of high value ingredients. We discussed about the dairy proteins, the enzymes, and the gelatin. We discussed about the advantages and disadvantages, not disadvantages, but mostly the advantages of the fermentation process. You will see there's more or less a repetition of some of the slides from the previous one, because I have to bring back you to that discussion. That's the reason why I brought these the same slides, some of them here. So it's also because of the low cost, the proven technology and scalability, the rapid production, the established R&D. Now there are a couple of things that we can definitely discuss here for these. Now let's talk about the low cost aspect of fermentation process. Why we call it a low cost process? Why it is a low cost process? No, you need. You're saying that it's not energy intensive, right? No, like if you're doing precision fermentation, it is actually very energy intensive. That's one disadvantage of precision fermentation. Okay, so that can be one. Any other? Just read the slide. What do you understand from there? The rapid production is there, but why the low cost? The low cost part I am talking about, the fermentation is widely used to produce industrial chemicals, feed ingredients, fuels, food products, and others. So if there is a technology that is used by multiple industries, so if I'm developing a product that I can sell to multiple consumers, will I increase the price or reduce the price? I have so many buyers, right? So that's why, because it is widely used, you have multiple players that are available in the market to make you the technology. So that's the reason why fermentation can be. But there are not many companies actually there are not many companies in the world that actually make reactors. It's just, I also say, I think this, because of the scale at which you can use them, you can develop more bulk products, you can reducing the cost of it. It's a very proven technology, scalability is there, that can also be there, of reduced cost. Now let's talk about precision fermentation. Now fermentation, as we all discussed, is a very old process, a biotechnological method which has been used in food production. During the introduction, Dr. Sabyasachi did tell you about breweries and beverages, the alcoholic beverages and non-alcoholic beverages that are being developed or produced using fermentation process. It is basically, or traditionally has been used to enhance the nutritional and the functional characteristics of food, improve the overall food sensory properties or food safety. So we improve the food sensory properties by producing the enzymes that can be used. So fermentation has been used to make those enzymes. Now precision fermentation is just an advanced version of the regular traditional fermentation process that we have. If you remember, we did talk about precision fermentation. I told you that the recombinant DNA technology was used to make it. So that was what the precision fermentation used to be. And then we started naming it as a precision fermentation. So because you can use recombinant DNA technology, so you're using molecular biology making modifications to the host, the DNA, you're adding your own DNA of interest, you can develop products. You can make your host develop products that are of your interest. So you can make different types of products. You can make proteins, you can make vitamins, you can make antioxidants. Rennet is a very good example. Rennet is used for where? Cheese. And rennet used to be produced from? It's very hard to hear, that's why I'm saying.
Calf intestines?
Okay. So initially, yes, but if you can do it through fermentation, you can make it consistently, right? It will have a consistent efficacy, and it is widely utilized everywhere. But that is also one of the product, rennet is also one of the product which has been developed through this recombinant DNA technology that has been approved by everyone. Every country in the world actually allows use of rennet. Human drugs like insulin is produced using recombinant DNA technology. Now, let's look into different types of the fermentations that are used in the food industry. So you have your traditional fermentation, you have your precision fermentation here, and then you have your biomass growth, just for the growth of the biomass. So microbes used, under anaerobic conditions convert sugar into end products with unique textures or flavors. So what you're using is, you're use traditional high value raw materials to produce end products. Example would be milk and produce yogurt. So end products minimally or not processed. So the end product is not processed. Yogurt, bread, tempeh, and alcoholic beverages are part of your traditional fermentation process. When you're looking at the biomass, that's where the mycoprotein comes into picture. So biomass itself serves as an ingredient. It uses novel, inexpensive feedstocks to produce high value proteins. Example, agriculture remains. So that's where your paralis can be used. So instead of like burning it, you can utilize that as a feedstock for growing some of the in the fermentation process to develop mycoproteins. And then comes the precision fermentation, where the host usually is not present in the final product. So the final product is developed by the host, but the host is not the final product. Sometimes yes, but not all the time. It uses novel, inexpensive feedstocks. We can use again the byproducts to produce the proteins. High purity, you require very high purity in that. If you're developing insulin for human consumption, let's say for human usage, it has to be very, very of high purity, right? It has to be clean. So for that, your downstream processing capital cost would be very, very high. So understanding this, which one would be costlier, fermentation or precision fermentation? So precision fermentation, yes, fermentation is advantageous. Yes, we can grow in bulk, but it's a highly processed product. The product that comes out from precision fermentation is highly processed. So you're adding cost to it. So this high cost, this low cost. I love this particular technology because it can utilize any bioresource that you have, any feedstock that you can provide. Even your food waste can be used to grow mycoproteins. This is something that we all should be looking at, honestly. With the current air quality indexes that you are seeing in different parts of this country, this can be one good example or one good unit operation that can be used. Now, how is the precision fermentation done? In precision fermentation, we use a host, and that particular host is called the factory, because that particular host is the one which is producing your product. And that host DNA is modified by introduction of a foreign DNA. The recombinant DNA technology is utilized. And what you are doing for that genome modification or genome editing, you can use this Cas9, which is basically going to cut the genome DNA at different locations. You can insert your your target DNA there in that particular location where the genome of the host has been cut. So you have your target selection. So upstream part will be your target selection, what you want to make. So proteins, lipids, pigments, vitamins. Then comes the host selection of the strain development. The host is selected for target expression and strain functionality is optimized. Question here for you all. Can all act as host? Like all the bacteria and the fungi and the yeast can act as host? For let's say if I have a product A, or like a specific protein that I would like to make, can I use E. coli for it, or should I be using yeast for it? Should I be using a fungi for it? How do I decide which host I should use? What would be the criteria for the host selection? Ease of extraction. You are talking about downstream processing part. Yes, definitely. What else? I'm still not able to hear you. Sorry.
Substrate for fermentation. Growth media.
The growth media?
The substrate for fermentation.
Substrate accumulation.
For fermentation, like.
Okay. Okay. What else?
The target product should be the part of its metabolism. If it's not produced,
If you do genetic modification, you can actually make it a part of its metabolism. That is what we are going to discuss tomorrow in synthetic biology. That's another. That would be systems biology. If you understand the biochemical factory which goes inside a microbe, you would be able to twist it, turn it in such a way that you would be able to produce the product of your interest. Yes, but why? How? What would be the other general requirement for host
It
selection?
should not be pathogenic organs.
Okay, it should not be
It
pathogenic
should not produce any metabolites which will react with the.
with the product.
products.
So it should not produce anything else other than your product. Let's say you should be able to produce your product first of all, and in good amount. Downstream processing, ease of extraction has to be there. What else? Oh, so you're talking about the moisture content part?
Yes, like we are gonna use fungi. We basically prefer a solid substrate based fermentation, where substrate is comparatively less that we use for a microbe like bacteria.
See, he actually brought up a very important aspect. Depending on the host, you will define what type of reactor you will use,
Yes,
right? So everything is related in this aspect of fermentation process, right? Many a times you might be use solid state fermentation process. You can use submerged fermentation process. Now, which one is cheaper, solid state fermentation or submerged?
submerged fermentation.
Okay, think about it again. Solid state fermentation is cheaper or submerged fermentation is cheaper? I made a face and then you are starting saying that. If you say submerged fermentation, you have to answer why. If you say solid state fermentation, you have to answer why.
Sir, submerged fermentation is scalable. We can scale it according to as per the at what scale we production want.
Okay.
But solid fermentation, we are like there are a lot of constraints regarding size, how to increase, manage, controllability. So might be submerged.
Okay. From the energy perspective, which one is cheaper? So if I'm looking from the energy, see, that's the thing. Depending on the question that I will ask, the answer will change. Like if you're looking for a production capability perspective, yes, submerged will be able to give you more. You can develop more products in that. It's scalable at a much higher rate than a solid state fermentation system. But from the energy perspective, solid state fermentation is cheaper as compared to submerged state. But that would be defined depending upon the host that you're using, or depending on the feedstock that you're using, right? Depending on the feedstock, the type of fermenter that you will use will change. There are different things that are interrelated here. Similarly, again, let's get into the feedstock selection. So you have to have the sugar or the industry side streams that can be used as our feedstock in the fermentation process. So these are done before you get into the fermentation. Then you're coming into the fermenter design. You have your submerged, the solid state, or the membrane cell recycled bioreactors. Now, when do we use membrane cell recycled bioreactors? When you are working with a very high value product. Then you come to the process optimization, the pH, the temperature, the oxygen or no oxygen concentration of the salt. Which of these fermentation systems between the submerged and the solid state, you would be able to have a much better control over the fermentation processes, like the pH, the temperature in the submerged, right? So again, depending on if your product or the host is not dependent on the pH, or if it is not dependent upon the temperature of the oxygen, not too much of variability in that, you might be able to select the type of fermentation system. Either you go for submerged or you will go for your solid state, right? And then comes the downstream processing. You might require some pretreatment, you might require separation, concentration, purification, product formulation. All of this adds to the cost, which is always going to increase. More and more steps are added, much more would be the cost. So now think again, in precision fermentation, we are making a very specific product, right, of a very high value. It's a very high value product. That means we need it of highest purity. If we need it for highest purity, our downstream processing would be more. So the cost of the product would be more. So it is a very nice technology, but it's also very expensive when we are looking at precision fermentation. This is my personal view. I'm not saying that this is a general view, but this is my personal view. My understanding about precision fermentation is that it's a costly process. Now let's look into the each and every aspect of the precision fermentation. That would be the target and the host selection. So the precision fermentation process starts with the selection of the target product. So you have to know what you want to make first, and only then you can decide whether you want to go through the precision fermentation or traditional fermentation process. So this is followed by the selection of the host that would be able to express the desired product. We already discussed almost all of this in the previous slide, but selection is also based on cost effectiveness. Which one would be cheaper for you? Now, ease of downstream processing was one of the answers, like easier extraction of the product. Now, host selection also requires a thorough understanding of the different metabolic pathways or for the strain development. Now, that was an amazing answer. Whoever gave that, thank you for that. If you understand the metabolic pathway, you can make changes to the host metabolic pathway to develop the product of your interest in more quantity. So new strains can use inexpensive feedstock. Now, if you make modification to the host biochemical pathway in such a way that instead of using sugar, it can actually develop an enzyme that can break cellulose or something else to get the sugar that can be used later on for the production of your product, you're reducing the cost. You're making a new strain, but you can use a different type of feedstock for your process. And then you can have an improved fermentation efficiency. That means shorter cycles and higher yields, and you can also have simplified downstream processing and better product recovery. Now, I'll give you a very, let me ask you a very simple question. What was you have heard about corn being used to make bioethanol, right? And there was this food versus fuel. This is a classic example that is given to everyone in the world. Whoever comes to the undergraduate or graduate life, you will hear about this food versus fuel. What was it? So when the corn was being used to make bioethanol, everybody wanted, because you will get more money out of it, people started growing corn for bioethanol production. So the cost of corn for human consumption, because availability decreased, the cost increased. It's a demand and supply thing, right? So that's the food versus fuel part in basic, like in the most layman way I can explain. But what is the biggest challenge? Was the efficiency of that corn being used for bioethanol high? The conversion efficiency, was it high? It was not. Why? Sorry, why do you think the efficiency of conversion of the lignocellulosic biomass, that is the corn stalks things, was less?
Will make more time.
Okay,
Time is
what's the
one.
biggest difference in plant cell and animal cell?
So actually, I am not that much. I am from mechanical background.
That is fine. Okay,
So
what is like if I give you steel and if I give you wood,
wood can break easily when
and then
compared
you
to
have a
this.
steel. So that's the biggest difference between plant cell and animal cell. Again, which one will break easy? Okay, biotechnology guys.
Animal.
It's easier to break the animal cells because you don't have a, in plant cells you have a cell wall and it's not easy to break them, it's not easy to digest them. So people started making modifications to the corn genome so that they can grow corn with walls or cell walls that can break easily when it comes into the mechanical process. That was one of the research, if I remember correctly, was being done by one of my friend long time back when I finished my undergrad. So think it from that perspective, like you have to do modification to the growth of the plant itself to get a feedstock. What if you can make the modification to the feedstock? Now that's a costly process. So if you can develop an enzyme that can actually interact and can break down the cell wall, break down and make it more available, the resources, make it more bioavailable for your host to grow, then yes, it is possible. So that is where genetic modification of the host itself sometimes is required to improve the overall productivity. C'est bon? When I say c'est bon, that's in French, it's like good. Correct? So you have to do genetic modification. So that is another important parameter when we are doing the host selection process here. Now you can look in from the table here. So for the bacteria, the prokaryotes are easier to manage. The cons are genetic drift, higher mutation rates. Now bacteria will mutate very quickly. And it has a very bad public perception. So if you say that, oh, I'm producing something from E. coli, people might not like it. So there are pathogenic E. coli, there are non-pathogenic E. coli strains that we use. Again, when you're looking at the yeast and the molds, it's slow generation times, which is a con for it. It could require more nutrients, and sometimes potential mold are pathogenic. Mycotoxins production is one of the issues that is there, and it has a negative impact on the product rheology. If you're using fungi, the rheology will change because fungi itself will add the texture to your product. Then it comes to the microalgae. You have target extraction challenges, which are presence of tough cell walls, which is silica-based coatings, and autotrophically grown, some like slow growth and low density. Oh, feedstock selection. The choice of feedstock is one of the major contributors to the overall cost. So we have already discussed this in detail for the process efficiency and the process sustainability. So as we go into the detail of the precision fermentation, the sustainability aspect of this whole course, this is where the sustainability part will come into picture, because we are trying to develop, or we are trying to choose feedstocks that are sustainable in nature. How do you define sustainability in one way or other? Give me the most layman definition of sustainability. So it is nice for the environment. How then what is sustainability? Break the word. Sustain and the ability to sustain. What is sustain? To maintain, like, see, it's not about to retain just the future. It's about you have a sustainable source to it, you have sustainable access to it, and it's always there, right? So you have the availability of that feedstock at all times, in the same quality, in the same consistency is maintained, and its impact on the environment is also sustainable. It's good, but it's also sustainable, it's maintainable, right? So that's where the sustainability is not just from the environmental aspect. Think about the accessibility and availability aspect to it. So accessibility, availability of the feedstock should be there. So that's where the food waste becomes a major source. It is an amazing source that can be used, but do you think food waste is a sustainable source? Just give me an answer, yes or no? So if you say yes, that means you are okay producing more waste. If you say no, then how it is sustainable? Every process has waste. That those waste can be used. I'm not talking about the waste that we generate. It's the whole process that generates. If that is something which will always be existing, we can use those waste as a feedstock. That is what the intent is, right? So then you have the conventional feedstocks, which are your standardized conditions, so no food safety issues, but it is costly to use, less sustainable. And example would be refined sugar, which is used for the fermentation process. Alternative feedstocks, not standardized. So that means our food waste is not a standardized waste or a feedstock that can be used. It would be different. So the batch that I might be getting from Punjab of all the let's say the lignocellulosic biomass will differ than the batch that I will get from Odisha, right? So I will not say it's standardized. It's a sustainable resource, but it's not standardized. There comes pre-treatments. That's why there is a little bit of cost which will get impacted there, because we might have to do some pre-treatment to make it consistent and standardized before we use it. Production inconsistency comes because it is non-standardized. And then regulatory challenges, food safety, because I don't know if I'm using food waste. So let's say if I go to the landfill area, I start taking all the waste from there to make some food products. Will you agree? No, because there are food safety concerns. You cannot use that as a food waste. Sorry, food waste as a resource for making your food products. So safety concerns have also been there. Then examples would be the side streams from the food industry. The lignocellulosic plant materials which are used in the fermentation. So leafy, woody parts of the plants remains after harvest, used for mycoprotein production. So that's where I was saying the paralis can be used for the mycoprotein production. The byproducts, food industry, the apple peel from the juice processing, that can be used for alternative proteins. Now apple peels, the citrus peels, do you think we'll be using that in the submerged fermentation or solid state? Apple peels, you have the apples, you have peeled the apples, the apple peels, potato peels, onion leaf, the peels, will you use it in submerged fermentation or solid state fermentation? Easier would be solid state. So depending upon it, you can change it. Like see, I have used onion peels for solid state fermentation for natural color. It's a cheaper process, but it's a longer process, but it's a cheaper process. Plastic waste, conversion of plastic to edible proteins by microbials after pyrolysis steps. So potential for various other applications that can be there. Agriculture crops, plant rich in carbohydrates such as sugarcane, can be used for alternative protein production. So these are some of the examples that you have. Any questions till now?
In the paralis which are generated from Punjab and Haryana and other state. So is there any research or ongoing research on the commercial viability of those paralis?
See, I cannot give you example on parali itself because I don't work here, but on agriculture byproducts, yes. So think about this way, if I may, because we are deviating a little bit from the topic, but it's an important question that you have asked. Because when we are using those as a feedstock, let's say for the fermentation process, we would like to maintain a consistency in the quality of the feedstock that we are getting. Semo?
Yes, sir.
So what happens? Okay, so think about this. So this is one field, a couple of fields that you have. what is the biggest challenge for the farmers? They are saying that they're not, they don't have the resources to collect it,
Yeah, balers and etc.
right?
Yes, sir. Time also, sir, because after the harvest and before sowing, there is only 15 to 25 days.
Yeah.
difference.
So now you think about in such a way. Now let's say if the commercial importance of that lignocellulosic biomass that is spread out on the field is very high. Do you think a company will pop up saying that, you know what, I will come and collect it? You just tell me the day that you have harvested, I will happily come. I will come even at the night and collect it. Do you think that will happen? If the commercial value of that particular feedstock is very high,
Yes, sir.
it will happen, right? So we have to first develop that commercial value. The only way you can do that is through research, where you can show that these lignocellulosic biomass are commercially viable and can be used to make products of very high value. So when you make products of very high value from a low value waste, the commercial value of that waste just went very high. And importance became very high, right? So that is what is needed. That is my personal point of view.
Yes.
That is what is needed for people to understand that these lignocellulosic biomass have a lot of commercial value. If it becomes, let's say, if you are able to establish a pre-processing facility in a specific district in Punjab, and it has collection facility that people from there will go to all these farms and collect it and bring it to that pre-processing facility. Now that pre-processing facility is basically collecting the products or the lignocellulosic biomass from all of these farms in one of the district, bring it to that particular pre-processing facility, and that facility is processing and making a consistent feedstock. Now that inconsistency has been fixed by consistency. What do I mean by it has been fixed? I will give you a very basic example. The orange juice that we were talking about, the real juice, the orange juice that you drink, do you think that orange juice that we get, if I take a batch of oranges from a farm, squeeze the juice out of it, will it have the same vitamin C, the sugar, the acidity that I will get, that I would have got last year, or that I will get next year? It will not, right? Industries don't work in that way. They collect all of that juice in a vat. Do you think this juice is pasteurized? It is pasteurized. So at what temperature? That's a very high temperature. I will not ask you to give me the exact value of the temperature, but it's higher, right? Yes, sir. Higher than 60, 70 degrees Celsius, or even 80 degrees Celsius. Vitamin C degrades at 40 degrees Celsius. So all the juice that you have just pasteurized, will it have any vitamin C left? So how do they make it consistent? They have to add it. So the food industry adds vitamin C after the fact. The aroma of the orange juice that you get, the smell of the orange juice that you get, the moment you open, you get an orangey flavor, right? You have just heated everything. Lemon has a fragrance, right? So lemon, which you squeeze on your salad, it gives you that aroma, the volatiles that comes out, it gives you that smell. If I heat it, will I still have that smell? So when I have pasteurized the orange juice, will I still have the smell? Technically, no. How do you add the smell? You add it. You don't add a smell gas, but you add the fragrance. Who makes that fragrance? Give me one fragrance company name. Don't give me Fog, other ones. Have you heard about Chanel?
Yes, sir.
Right?
Yes.
Coco Chanel?
Yes.
Chanel makes fragrances for food industry. The smell that we get in our juices, in many of our food products, is actually made by Chanel. It's actually costly. So what you eat contains a lot of this. So that is adding consistency. So in the end, the product that is going to the consumer is consistent. You're getting my point where I'm taking you. I gave you that example to explain that you get the feedstock from different sources, you bring it, you process it, you pre-process it, you process it in such a way that you get a consistent feedstock, and then that particular industry will sell it to the bigger industry that, hey, here is a feedstock that you can use. So now you have added value. So this industry is making money from the bigger industry. The farmers are making money from that collection industry. That's where you add the value. Okay?
Yes, sir.
That was the question, right? Okay, let's get into the fermenter design. Sometimes we are deviating away from it, but it's a very interesting conversation. Thank you. Now, fermenter design, optimization, and scale up. So the type of bioreactor which is selected is based on their ability to meet the specific requirements of the process or the product that you are trying to grow or the product that you are trying to obtain. So the type of bioreactor you are going to use will change. It also depends on the target products, the host that you are going to use, what type of host, what are the conditions that it requires for its growth, whether you're going to use submerged or the solid state fermentation system. So, but then that's where you'll see that you have the lab scale where the screening is done. Then you go into the bigger lab scale. So you go 2 liters or 5 liter fermentation system. So in-house process simulation and optimization. This is where majority of our research goes. So if you come to my research group, a colleague of mine, we bought like 2 bioreactors of 5 liters each. So we do this type of the lab scale bioreactor design, bioreactor application, and then we get into the pilot scale, and that pilot scale can be scaled up into the industry scale value. So optimization of the process parameters such as the temperature, the pH, the oxygen supply, or sometimes you might not require an oxygen, so you might require a completely anaerobic condition. So this all affects the overall cost and sustainability of the process. Okay? Okay, which one is cheaper, anaerobic fermentation or aerobic fermentation? It's a very genuine question. It's a very simple question. Which one do you think is cheaper, aerobic or anaerobic? Aerobic? How many of you are saying aerobic? Only 3? Yeah, I can say only 3, 4. How many of you are saying anaerobic? Again, similar numbers. You're equal in numbers. Why? Okay, if anaerobic, why? If aerobic, why? Sparging air, there is a separate need. Oxygen. So do you add oxygen through air or do you add oxygen as an oxygen? Is costly or cheap? That adds cost, right? So aerobic processes are costlier as compared to anaerobic processes. That's where only the cost factor comes in. Nothing else will change. Aerobic processes are a bit costlier than anaerobic processes. Now, some of the applications and the challenges with respect to the fermentation would be some of the challenges that need to be overcome when we are looking at precision fermentation specifically would be the new strain development and the sustainable feedstock. Because if you can develop strains that can consume feedstocks that are waste materials, that would be amazing. You are going to reduce the overall cost. The process scalability with the large investments and overcoming public perception is key. Precision fermentation requires recombinant DNA, right? You are basically genetically modifying your organism. So the product that you are producing is coming out from a genetically modified organism. So public perception is, I don't use GMOs. So your product will not have any traction in the market. So you're basically you have to convince the public that the product that you're developing is good, right? That notion has to be overcome. So new fermenter designs are required to meet the needs and the regulations. We need to convince the regulatory authorities on product quality and safety. Now that's where the FDA, the EU, Food Safety, FSSAI in India will come into picture if they allow GMOs or if they don't allow GMOs into the market. And if they do, what are the criteria? You have to meet all those standards, all those criteria. So these are examples of some of the products, the status quo with what is happening with them. So for the dairy, it meets the need for the animal-free milk, proteins with the same composition, taste, benefits as animal ones by using more production, sustainable with the most advanced and skilled way. It's a very cost-effective, demanding on a purification process, because the moment you're looking at making dairy-free milk, you're looking at producing protein, and those protein has to be processed. The downstream processing, you need highly purified proteins to make that product. So your downstream processing cost will go up. Similarly, other examples are there for the fats, the oils, and the eggs. Then comes the regulatory authorities part. So where you are looking at the EU, so you have the EFSA, and on the US side you have the FDA. So FDA has a requirement that the ingredients that you're using in your product development, if they are GRAS, that means generally recognized as safe, it will get the approval. EU is way much more stricter as compared to US from the food safety perspective. They don't allow genetic modification. In many of the countries won't even allow you to sell GMOs. So they are very strict in those nature. So that's where the market, if you are developing a product that is coming out of a GMO, you don't have a very large market then if the public perception is not changed, or if you're not able to convince these regulatory authorities. Good Food Institute that I named in the previous presentation is one of the lobbying group that actually lobbies in the favor of alternative protein industries, the precision fermentation industries, and the cultivated meat industries to these regulatory authorities, trying to convince them that it is safer from the product quality perspective, and it's also safer from the environment perspective. Now, there are also changes. There will also be certain regulations with respect to the labeling process, which would be involved, whether you're using GMOs, non-GMOs. Some countries will allow you to write that you have to mention GMOs. Like in India, you have those green dots, red dots. If it is vegetarian, you have to have the green dots. If it is non-vegetarian, you have to have the red dot. Am I correct? So those type of regulatory combinations have to be used. Now, the industry and the market landscape, you have already seen one of the slides where the meat, alternative meat or the plant-based meat substitute requirement or the market is increasing. And there are also a lot of companies that have come into picture with respect to the precision fermentation. Now, the market is expected to grow from 1.6 billion, which was in 2022, to almost 36 billion in 2030. So it's a market that is still growing, and precision fermentation is being used for alternative meat, so alternative protein generation or protein production. So it's a growing market. So if you're interested to look into for startups in this industry, this is the time. The time is ripe for you to get into that. Now, the few of the key takeaways from this whole presentation today would be the precision fermentation process is a technology that is rapidly being adopted by food tech companies. There is a continued growth of alternative proteins and the meat industry, and it will provide the required push for the precision fermentation. The technology enables food producers to efficiently create specific proteins, lipids, vitamins, enzymes, pigments, and more using microbes instead of animals. You have substantial room for innovation. The key challenges that still pertains with respect to precision fermentation would be the strain development, the host selection, the strain development, alternative feedstock for sustainability, process scalability, proper infrastructure, consumer education, and regulation. So if you're able to at least fix 40 or 50% of all of these challenges, you would be able to have a very huge market for this. I hope you have understood or you have got some idea about precision fermentation, cellular agriculture. Thank you. That would be it for today.